Curious how the internet actually works? Let's dive into the world of networks, where every email, stream, and connection happens.
Today, we're diving headfirst into the fascinating world of computer networks. Don't worry, we're starting with the absolute basics.
That's right. We'll be your guides through the intricate web of connections and all those signals that make up the digital landscape. Basically, how the internet works, from sending emails to streaming your favorite shows.
Exactly, and we've got excerpts from a stack of networking textbooks ready to be unpacked and analyzed. By the end, you'll not only impress your friends with your newfound knowledge, but you'll gain a deeper understanding of the tech you use every single day. Ready to jump in?
Let's start by answering a fundamental question. What exactly is a computer network? Imagine a system like the Postal Service, but instead of letters and packages, we're talking about data. At its core, a network is simply two or more computers linked together, allowing them to exchange information.
Okay, that makes sense.
Yeah.
And just like postal systems, networks can be big or small, right? I mean, I have network in my apartment with my laptop and printer, but then there's the internet, which connects millions of devices.
You've got it. Your home Wi-Fi setup connecting your devices. That's a local area network, or LAN. And you're right, the internet is a massive network, a network of networks spanning the globe.
So we have these networks, but they're not just a jumble of wires and signals, are they? There must be some serious organization behind the scenes.
You're right, it can get complex. To manage this, networks use a layered structure. Think of it like building a house. You have the foundation, the walls, the roof. Each layer has a specific job, and they work together to create a functional structure.
So instead of throwing every task at a network all at once, it's divided into smaller, more manageable chunks.
Precisely. This layered approach makes networks easier to design, implement, and troubleshoot. Plus, if you want to upgrade a specific part, say, switch from copper cables to fiber optic, you can do so without redesigning the entire system. This modularity is key to the internet's flexibility and growth.
That's incredibly clever. So how do these layers actually work? What are they responsible for?
Well, the most common model for understanding network layers is the OSI model, which defines 7 layers. Don't worry, we won't delve into all of them today. But to give you a taste, the bottom layer, the physical layer, deals with the actual transmission of raw data as signals over physical media.
So we're talking about the physical stuff, like the cables we see?
Yeah.
What about Wi-Fi? Is that part of the physical layer too, even though it's wireless?
Absolutely. The physical layer encompasses both wired and wireless mediums. Whether it's copper wires, fiber optic cables, or radio waves carrying Wi-Fi signals, this layer ensures the physical transmission of those ones and zeros that make up data.
That's incredible. I've always wondered about Wi-Fi sending data through the air. Seems magical. But I imagine each medium has its pros and cons. Like, fiber optic cables are probably much faster than traditional copper wires, right?
You're right. Fiber optic cables transmit data as pulses of light, making them significantly faster than copper. However, they can be more expensive and delicate to handle. On the other hand, copper is cheaper and more durable, making it suitable for shorter distances, like within homes and offices.
It's like choosing the right tool for the job. Fast fiber optics for long distance, high-speed connections, and reliable copper for shorter everyday connections. So we've got our data racing along these physical channels, but let's face it, things don't always go as planned. What happens when errors occur during transmission?
That's a crucial point. Just like a game of telephone, data can get garbled along the way. Noise, interference, faulty hardware, all these can introduce errors.
So it's like static on a phone line, or when my internet connection drops during a storm.
Exactly. To combat this, networks employ clever error detection and correction mechanisms. Think of it like having a spell checker for your data. One simple technique is parity checking.
Parity checking. I'm intrigued. Tell me more about how it works.
Imagine you're sending groups of bits, those ones and zeros. In parity checking, an extra bit, called the parity bit, is added to each group. This bit acts as a flag, indicating whether the total number of ones in that group, including itself, should be even or odd.
Okay, so it's like adding a check digit to a credit card number. If the digits don't add up correctly, you know there's an error. But what if an error is detected? Does the entire transmission have to start over?
Not necessarily. That's where error correction comes in. There are more sophisticated codes like the Hamming code, which can not only detect but also correct single-bit errors without needing a retransmission.
That's remarkable. So we have these systems working behind the scenes to ensure our data arrives intact. But how does the network know where to send the data in the first place? It's not like every device has a direct line to every other device, right?
You're right. That would be chaos. This is where MAC addresses come into play.
Wait, MC addresses, like on my laptop. I thought we were talking about networks, not computers.
It can be a little confusing, but in this context, MAC stands for Media Access Control. Think of it as a unique identifier assigned to every device that can connect to a network. It's like giving each device its own unique phone number within that network.
So even within my home Wi-Fi network, each device, my phone, my laptop, even my smart speaker, has a unique MAC address. What's the purpose of having these unique identifiers?
Imagine a room full of people trying to talk at the same time. It would be impossible to understand anything. MEC addresses help to prevent this kind of chaos on a network, especially in shared medium networks like Ethernet.
Ethernet, like what's used for wired connections. So how do MSC addresses help manage all those devices trying to share the same cable?
In Ethernet, a method called CSC-MSED, or carrier sense, multiple access with collision detection is used. It's like having everyone in that crowded room politely taking turns to speak. Devices listen to the network before transmitting data. If the network is idle, they can transmit. If it's busy, they wait their turn. And if by chance two devices transmit simultaneously, a collision is detected and they back off, rescheduling their transmissions.
It's a continuous, organized dance of data packets, all thanks to these MMAC addresses and protocols. But what about when data needs to travel beyond my home network across the vast expanse of the internet? That's a whole other level of complexity.
You're absolutely right, and that's where routing comes in. But I believe it's time we take a pause and delve into that fascinating world in our next part. Welcome back. We left off talking about data traveling within a single network, like your home Wi-Fi. But what happens when you send an email or load a website, sending data across continents? That's where routing comes in.
It's mind-boggling when you think about it. Countless data packets zipping around the globe, finding their way through a maze of networks. How does it all work?
Think of routing like a GPS system for your data. Special network devices called routers act as guides, using information about network addresses to determine the best path for each data packet.
Network addresses, like those IP addresses we hear about.
Exactly. Every device connected to the internet has a unique IP address, like a digital street address. When you send data, it's labeled with the destination IP address. Routers use this information, along with their routing tables, to figure out where to send the data next.
Routing tables, what are those exactly?
Imagine a roadmap that each router keeps. This roadmap, or routing table, doesn't list every single IP address on the internet. That would be impossible. Instead, it contains information about network prefixes, like area codes for IP addresses.
So instead of knowing the exact address of every house, the router knows which direction to send data based on the city or zip code.
That's a great way to think about it. This hierarchical system allows routers to efficiently forward data packets without needing a complete map of every device on the internet. And to make things even more efficient, these routers talk to each other, exchanging information about the best routes based on network conditions.
So it's like a network of traffic reporters constantly updating each other about accidents, construction, and the fastest ways to get around. What if there's a traffic jam on one route? Can the data just take a detour?
Precisely. Routers use clever algorithm, like Dijkstra's algorithm, to calculate the shortest and most efficient paths. They consider factors like network congestion, bandwidth availability, and even cost, dynamically adapting to changing conditions.
Dijkstra's algorithm sounds intense. Is that how mapping apps find the fastest routes for drivers?
You're on the right track. It's a classic shortest path algorithm used in various applications, from computer networks to mapping apps and transportation logistics.
That's incredible. But speaking of traffic jams, what happens when a network gets congested? Like when everyone's trying to stream the big game at the same time? Does the internet just grind to a halt?
Not exactly, but things can definitely slow down. This congestion happens when too much data tries to travel over the same network link simultaneously. It's like trying to fit too many cars on a single lane of highway.
So just like in real-life traffic, you get bottlenecks and slowdowns. What can be done about it?
Networks use congestion control mechanisms to manage these situations. One method is called back pressure.
Back pressure. Does that mean pushing back on the data flow?
Exactly. When a router detects congestion, it sends signals back to the sending devices, essentially telling them to slow down their data transmission rate. It's like saying, hold on a second, let me clear this backlog before you send more.
That's a clever way to prevent a complete meltdown. So we've got these routers working tirelessly behind the scenes, guiding our data packets, adapting to changing conditions, and even managing traffic jams. It's like a well-oiled machine, but much more complex.
And there's another layer of complexity we haven't even touched on yet. how different applications share network resources and ensure reliable communication. This is where the transport layer comes into play.
The transport layer. It sounds like we're moving up the ladder of abstraction. Tell me more about what happens at this level. We've journeyed through the physical cables, navigated the world of MSE addresses and routing, and now we've reached this mysterious transport layer. It feels like we're getting closer to the magic of how we actually experience the internet.
You're right. This is where the raw data packets we've been talking about are transformed into something meaningful for the apps and software we use every day.
Okay, so if I'm sending an email, the transport layer takes the data from the lower layers, packages it up properly, and makes sure it reaches my email app instead of, say, accidentally opening a video game.
Precisely. It ensures that data is delivered reliably and in the correct order to the right application on the receiving device. It's like having a dedicated mailroom in a massive office building, ensuring each department gets the right mail.
And just like with mail delivery, I'm guessing there are different levels of service.
You're catching on. In the transport layer, two protocols take center stage, TCP and UDP. They have very different approaches to data delivery.
Oh, here we go again with the protocols. I'm ready to hear about TCP and UDP. Lay it on me.
TCP, or Transmission Control Protocol, is like that meticulous mail clerk making sure every piece of mail is accounted for and delivered in pristine condition. It's a connection-oriented protocol, meaning it establishes a dedicated link between the sender and receiver before transmitting data.
So it's like scheduling a courier pickup. They confirm the pickup and delivery addresses before taking the package, ensuring it reaches the intended recipient.
Exactly. And like a diligent courier service, TCP provides reliable data delivery. It tracks each packet, checks for errors, and resends any lost or corrupted data. This makes it ideal for applications where data integrity is essential, such as email, file transfers, and of course, secure online transactions.
It makes sense that something as important as online banking would rely on the meticulous mail clerk of protocols. So what about UDP? What's its role in this digital mailroom?
UDP, or User Datagram Protocol, is more like sending a postcard. You drop it in the mailbox and it eventually reaches its destination, hopefully. It's a connectionless protocol, meaning it doesn't bother with establishing a dedicated connection before sending data. It's all about speed and efficiency.
So UDP is the fast and loose approach to data delivery. That sounds risky. When would you ever choose speed over reliability?
When the content is time-sensitive and some data loss is acceptable. Imagine streaming a live sporting event. A few dropped packets might mean a momentary glitch in the video, but it's better than constant buffering or lag, right? UDP is also great for things like online gaming, where speed is crucial for a smooth experience.
That makes sense. I'd rather have a little blip in my game than experience delays that throw me completely off. So we've got TCP for reliability and UDP for speed. It's amazing how these protocols cater to such different needs.
Yeah.
But what happens once the data reaches the right application? Where do we go from there?
We've finally reached the top floor, the application layer. This is where the network meets the software you interact with daily.
So we're talking about things like web browsers, email clients, video streaming services, all those apps that make the internet come alive for us.
You got it. This layer is home to a vast array of protocols that enable specific applications to communicate over the network. For instance, HTTP, or Hypertext Transfer Protocol, is the language of the web. It's how your web browser talks to web servers to fetch and display web pages.
HTTP, that rings a bell. It's like when I type a website address into my browser. My browser uses HTTP to request the website data, right?
That's exactly how it works. And just like different countries might have different languages, various application protocols are used for different purposes. Email uses protocols like SMTP for sending and POP3 or IMAP for receiving.
So it's like a global village with everyone speaking different languages, but the underlying network infrastructure ensures everyone can communicate and share information.
A perfect analogy, and that, in a nutshell, is the journey of data through the fascinating world of computer networks.
Wow, we started with physical cables and somehow ended up in a global village of interconnected applications. It's mind-blowing how all these layers and protocols work seamlessly together.
And we've only scratched the surface. The world of computer networks is vast and constantly evolving. But hopefully, this deep dive has given you a solid foundation for understanding how it all works.
It certainly has. We've learned about the layered structure of networks, explored the intricacies of routing and congestion control, and even met the key players in the transport and application layers. It's been quite an adventure.
And remember, this is just the beginning of your journey. There's a universe of knowledge out there waiting to be explored.
So to our listeners, we encourage you to keep that spirit of curiosity alive. Dive deeper into the topics that fascinate you, explore the inner workings of your own devices and networks, and never stop asking questions. Until next time, happy networking.